So good morning everyone. Welcome to Kaexchem. And in this actually somebody told me to be more enthusiastic. So good morning everyone. Welcome to Kaexchem. And in this lecture we will be covering chemical equilibrium in we will see how many minutes. And I have all the slides prepared for you. And this is for JEE Main's NEET all bits that and all the best for the coming exam. So let's begin. This lecture is not for first timers. It's a revision. Anyways, first of all, we can say that we can classify them on the basis of their reversibility, whether those reactions can be reversed or not. If they're irreversible, they are shown like this. Here's more points that I have written. Do keep in mind, limiting reagent can only be defined in irreversible reaction, can't be defined in case of reversible reaction. And here's some examples for both of them. Now, homogeneous and heterogeneous. In homogeneous reactions, all reactants and products are in same phase. Heterogeneous, they are not in same phase. Fast reactions are generally ionic, and slow reactions are generally covalent or molecular. Exothermic reactions have heat released, endothermic reactions have heat absorbed. All of this is very obvious. Most of you already know this. If you don't, consider studying chemistry from scratch. But let's continue. Chemical equilibrium. What is chemical equilibrium? It is basically the state at which every measurable property, I have written properly, wow, every measurable property of the closed container in a reversible reaction. Basically, equilibrium cannot be attained in the irreversible reaction. Just like in thermodynamics, if we do an irreversible process, then the system never has time to attain equilibrium and the process is very fast. But if we talk about reversible gas expansion, I was talking about gas expansion. So if we talk about reversible gas expansion, then it is a quasi-static process in which if it is reversible, every stage there is equilibrium. The system tries to attain equilibrium. So similarly here, equilibrium can only be defined or come into light when we're talking about reversible reactions. And what measurable properties are constant? For example, concentration of all substances, reactant or product, the pressure in the beaker, density, color of the beaker, temperature, and any other thing that you can measure macroscopically will be constant. Okay. And of course, at chemical equilibrium, rate of forward reaction equal to rate of backward reaction. Also, this does not mean that the reaction has stopped. It is still dynamic. It is still happening at the molecular level. I have added an analogy. It's like if there's a water tank, it is being filled and emptied at the same rate. How activity is still happening, but the level of water is constant. And if we add a catalyst to the beaker, then catalyst only makes the attenuation of equilibrium faster, and it cannot alter the state of equilibrium. We will look at this in detail. These are graphs that you must know. And keep in mind that this products line need not be above the reactants line. They can also be like products here and reactants here. Basically, what this graph wants you to tell is there will be no change in amounts at equilibrium. These lines will become straight. Okay. Now let's talk about physical equilibrium. You might not have seen this topic in any of your classes, but it is important to understand. Basically, physical equilibrium is when more than one states of matter, they coexist at a fixed temperature. For example, solid and liquid equilibrium, we have solid water, ice, convert into liquid water, and in physical equilibrium, rate of melting of ice is equal to rate of freezing of water. So activity is still happening, but both ice and water are coexisting. Similarly, liquid gas equilibrium, rate of vaporization is equal to rate of condensation. And for this kind of equilibrium, system must be closed and the temperature must be constant. And basically the rate of vaporization is constant from the beginning, but the rate of condensation starts from 0 and slowly it catches up. That is how this liquid gas equilibrium is attained. Okay. Solid gas equilibrium, some solid directly turn into gas on heating. For example, kapoor, camphor. This is sublimation, like they completely skip the liquid state, and when you cool that gas, it gives back the solid, which process is called disposition. Okay. And there are some liquids that turn into solids when they are heated. For example, basin ke pakode. Otherwise, liquids are always turned into solids, their solid form, when they are heated. Okay. When they are cooled. No, what? When they're cooled, yeah. Anyways, according to NCERT, ammonium chloride, iodine, and camphor are such solids which directly turn into gas on heating. Okay. I have never seen liquid iodine. Anyhow, solution equilibrium. Basically, the solute in a saturated solution, you should know what a saturated solution is, exhibits equilibrium with the solvent. Basically, what happens is that, there's a solute is dissolved in the solvent, and there is some solute which is undissolved in the solvent. So the dissolved solute and the undissolved solute, it keeps exchanging places with each other. And both of these processes, like the undissolved going into dissolved state and dissolved going into undissolved state, processes which are called dissolution and precipitation respectively, they happen at the same rate, and the same equilibrium can happen for gas and liquid. Now we come to the core of this chapter, which is the law of mass action. Basically, here we have considered a reversible reaction. A moles of A with B moles of B gives C moles of C and D moles of D. I have used small letters to denote stoichiometric coefficient. And you must know a little chemical kinetics here, that the rate of forward reaction will be shown as rate constant of forward reaction, and keep in mind that this is small k. So small k forward, rate constant of forward reaction into the concentration of the first reactant raised to its stoichiometric coefficient multiplied by the second reactant expressed the same way, and the rate of backward reaction is shown as rate constant of backward reaction into the, basically defined as the same way, the reactant itself, its concentration raised to its stoichiometric coefficient. Okay, yeah, so keep in mind these are small k's because the capital K is used for the equilibrium constant. Now, what is the equilibrium constant basically? Since here we are talking about concentration, we'll use Kc. You will get to know that this has a twin called Kp soon. And at equilibrium, basically, rate of forward reaction is equal to rate of backward reaction. So if you set these quantities equal to each other, you get that this expression, product of the products raised to their individual stoichiometric coefficients divided by reactants expressed in the same way, is known as the equilibrium constant or the concentration equilibrium constant, Kc. And basically, this is another expression. If you have been given rate constants of forward and backward reactions, you can use this formula to find out the Kc as well. Now let's learn in detail about the equilibrium constant. Basically, the only physical property that can change the equilibrium constant is temperature, which means that in a vessel, Kc will always remain constant unless you change the temperature. It is not affected by concentration. If concentration of one entity is changed, the others adjust to keep the K equilibrium same. This is the kind of aura the equilibrium constant holds, and hence keep in mind that temperature is the only thing to alter it. And if the reaction happens to be athermal or does not release or absorb heat at all, then temperature cannot affect the equilibrium constant. Then it becomes a universal truth. And keep in mind that only gas entities are kept in equilibrium constants. Do not consider solids and liquids unless the question asks you to do so. For example, in homogeneous equilibrium. If you are given liquids in homogeneous equilibrium, you have no choice but to account for them. But normally the concentrations of solids and liquids are so large that we don't consider them a part of the equilibrium and take them as one. Okay. I defined Kc in section 5. It uses concentration, and Kp, its twin, is basically, it uses partial pressure. So instead of writing capital C raised to the power C, we will do partial pressure of C raised to the power C, partial pressure of D raised to the power D, divided by reactants expressed in the same way. And this is what Kp is. Okay. And remember this quantity, whenever I will say delta N, it means the number of gaseous moles on right hand side minus number of gaseous moles on left hand side. Basically, the emphasis on gaseous is because we want to ignore the solid and liquid moles. Okay. Because I just told you they are not significant. So for any reaction, if you want to find the unit of Kc, it is going to be mole per liter raised to the power delta N. Kp will be atm raised to the power delta N. Atm is atmospheric pressure. And remember this expression that Kp is nothing but Kc into universal gas constant into absolute temperature of the vessel raised to the power delta N. Now, Bhavya, what is partial pressure? What is this partial pressure? A lot of you may not know what partial pressure is, especially if you are in 11. So basically, partial pressure of a gaseous substance is its mole fraction or in the mixture into the total pressure exerted by the mixture. And the sum of the partial pressure of individual components is what we call as the total pressure of the solution. Okay. We will dive more into this. First of all, let's look at this question. At 700 kelvins, the equilibrium constant Kp, partial pressure, for this reaction is itna. What is the value of Kc at the same temperature? So, What the examiner expects you to do is use this expression. Okay. If we use this expression, we know delta n is 3 minus 2. How? We see there's one gaseous mole, two gaseous mole, total 3 on right hand side, and two gaseous moles on left hand side. So 3 minus 2. So this comes out to be 1. This comes out to be 1. So Kp is nothing but Kc into RT. Okay. And at a certain temperature, the dinitrogen tetroxide N2O4 dissociates into nitrogen oxide according to the following reaction. And at equilibrium, total pressure of the system is found to be 2 atm and mole fraction is 0.4. What is the numerical value of Kp for this reaction? I have written the way. I'll basically use a screenshot from Gemini and I provided you a cleanly formatted solution. Just see how it works. First of all, we see the mole fractions. Mole fraction of NO2 is given. NO2 mole fraction is given to you. And since there's only two components, if we subtract this mole fraction from 1, we get the mole fraction of the other guy, basically N2O4. And how do you calculate partial pressure? I just told you it's mole fraction into total pressure. So total pressure is given to you 2 atms. So multiplying by the individual mole fractions, we get the partial pressures. And using the expression that I just talked about, we can calculate Kp easily. Okay. Now let's look at the algebra of the equilibrium constant. How does the equilibrium constant change when we alter the stoichiometry of the reaction? Basically, for all of these cases, I am going to say that let K be the original equilibrium constant for the reaction, A converts to B, and K dash be the new equilibrium constant. And basically, I have described some changes here. All the following changes occur when altering only the stoichiometry of the reaction. Basically, if I express this reaction in the opposite way, I reverse it, then the new equilibrium constant is reciprocal of the original one. If I multiply n on both sides, then the equilibrium constant gets raised to power n. If I divide by n both sides, it gets raised to power 1 by n. And if we add a reaction here, like in the same vessel, we add C converts to D, and this reaction on its own has an equilibrium constant of K naught, then the net reaction has an equilibrium constant K dash is equal to K of the first reaction into K naught of the second reaction. And this is the effect of temperature. This is the reaction. What I'm saying, this is the expression which you have to use when you account for change in temperature in an equilibrium. And basically what happens is that, say, K1 is our rate constant at temperature T1 and K2 at T2. Delta H is the enthalpy of reaction taken with sign. So the log of K2 by K1 or log K2 minus log K1 is going to be equal to delta H by 2.303 R into 1 by T1 minus 1 by T2. Now it's evident that K will increase with temperature if reaction is endothermic and K will decrease with temperature if reaction is exothermic. This is a consequence of the Le-Chatelier principle, which we will learn at the end of the lecture. And keep in mind that this is assuming that delta H is independent of temperature, assuming, which is sometimes not true. And this is what we call the Van 't Hoff equation. Okay. And just keep in mind how to draw graphs for this. I think you are smart enough that you can look at this expression and dissect it to find graphs. And keep in mind temperature is kept in kelvins, not Celsius. I see a lot of you make that mistake. And now let's look at applications of equilibrium constant. Basically, it can be used to predict extent of reaction if it is greater than 10 raised to the power 3. Concentration or partial pressure of product much greater than reactant. And if it is less than 10 raised to the power 3, the concentration of reactant is much greater than product. And let's define. It looks kind of messed up here. Basically QC. Okay. What is QC? Even in, what a word, unequilibrialized state, we can define Q. Same form as here. Basically, let's look at this reaction only. Let's say it is not in equilibrium. Still, we can write the equilibrium type expression for it. B into D upon A into C. Keep in mind that we are considering this as not in equilibrium. So we will not call it K, we will call it Q. Okay. Basically, what happens is that if Q is less than K, the reaction still has to go forward till Q is equal to K. You see where I'm going with this? If Q is greater than K, reaction goes backward till Q is equal to K. You know, equilibrium is the state in which the solution has the least amount of energy. And in any physical process, if there is no external work being applied or if there's no external agent, every system tries to minimize its energy to increase its stability, which is why reaching equilibrium is a spontaneous process no matter whether you lie on the left or the right side of it. And this graph illustrates exactly that. You see, this is a graph of reaction quotient Q with time. If Q is greater than K, it will change till Q is equal to K. And the similar thing happens when Q is less than K. Okay. So keep in mind applications of equilibrium constant. Now this is a topic I added on my own. I could have ended the video right here, but I didn't because I see a lot of you struggle with this. So we are going to look into detail the degree of dissociation and reaction profiling. Reaction profiling is an art which, if mastered, can bring this chapter and also ionic equilibrium, electrochemistry, redox reactions, all of this on your fingertips. Okay. So, and also solutions, basically chemical kinetics, everything will be on your fingertips if you master the art of reaction profiling. What is degree of dissociation? Degree of dissociation for a reactant, it is always defined for reactants. In a reversible reaction, is the fraction of it that is broken down. Let's go into more depth. A reaction profile is a table like this, which shows the status of different participants at different times. Here's an example. Let's say AB. Keep in mind all of this is gases. So AB breaks down into P moles of C and Q moles of D. Let's say the concentration of AB, not concentration. Let's say moles of AB at T is equal to 0 was J. I know it's a weird variable, but I am weird too. So at T is equal to 0, the number of moles, I have written concentration because even I get confused. The number of moles at T is equal to 0 of AB is J. And since the reaction hasn't started, C and D have no moles yet. And let's just say that J, this is J minus J alpha. Okay, now you see where I'm going with this. This is the part that broke off. Alpha J is the part that broke off and alpha is the fraction. So if I take J common, it will look like this. And if J alpha part is broken, if J was fully broken, it would make PJC and JQD. I have chosen very unconventional variables. Basically, PJ alpha C is made and QJ alpha D is made because J alpha AB has broken. Following the stoichiometry of the reaction, this is how much C and D have formed. So I have explained in the text as well. Alpha is the degree of dissociation and J is the moles of AB at T is equal to 0. The fraction of AB that broke is alpha J. As you know, this is wrong. I have written it in a wrong way. Alpha is the fraction. Alpha J is the net amount that broke. Alpha is the fraction. Okay. So if J moles of, according to the reaction, if J moles of AB had fully broken, it would give PJC and QJ moles of D. Since here's J alpha moles that broke, here's P alpha J C is made and Q alpha J moles of D is made. And this logic is what you have to extend to solve questions properly. Practice more and more and you will get muscle memory of doing reaction profiling. And keep in mind that percentage dissociation is 100 times the degree of dissociation. That's easy to understand. Reaction profiling is very useful, but remember some things when using it. The equilibrium constant is defined on concentration, not on moles. Don't go around applying the equilibrium law of mass action to the number of moles directly. It will give you the wrong answer in most cases. You may mess up by not taking the volume in consideration. What separates the number of moles from the concentration? It's volume. So how do we know what's the power of volume that we have to add? Basically, let me help you with that. You write your normal Kc expression in terms of moles. Keep in mind, I have written this in terms of moles. And the trick here is that you multiply 1 upon V raised to the power delta N for Kc. And if you are dealing with Kp, you just multiply the total pressure upon the summation of gaseous moles raised to power delta N. And how do I remember this? Pv is equal to nRT. So if you remember that V is at the bottom in Kc, then it's no issue for you to understand that, and if I do 1 upon V, this will turn into P by N. So P by N is here. It comes directly from the ideal gas equation. Isn't that beautiful? And you would say that also RT raised to the power N term should come. N term should come. Remember this expression. It all cancels out in a very beautiful manner, my friend. So just write this in terms of the moles and multiply these things raised to the power delta N. What is sigma N here? It is the total moles at equilibrium. Only considering gas moles, which in this case is this plus this plus this. Basically, the moles of all the gaseous participants at the equilibrium state. And that's it. We are done with reaction profiling. And remember this formula if it is asked. For a dissociation like AN breaks into Na, the observed molar mass of A is original molar mass of A divided by the summation of moles at equilibrium. Now let's move on to the last part of this chapter, which is the Lake-Chartier's principle, the most beautiful concept this chapter has to offer. Basically, if a change is applied to a system in equilibrium, it will shift in a direction to oppose the change. and form a new equilibrium under new conditions. Does this remind you of something? In physics, basically if you are in 11th you wouldn't know, but the 12th class people and the droppers would know that something in physics, there's the concept of electromagnetic induction, where a coil resists the, I forgot the exact concept, I'm not good at physics, but basically same thing happens. If a change is applied to a system, it will shift in a direction to oppose the change and form a new equilibrium under new conditions, which accommodates the change applied to the system. How come? Well, if let's see the effect of change in the concentration. We discussed this earlier as well. Basically, in a reaction, if reactant is added, more reactant is added, equilibrium shifts to right direction. Basically, reactant is added, so it reacts it to form more product to keep K constant, and equilibrium shifts towards right side, and vice versa. If product is added, it shifts towards left side. And the addition of solid does not affect equilibrium. We know why. If we add a catalyst, basically nothing happens, but time taken to attain equilibrium is less. The state of equilibrium is not affected. If the catalyst is the same phase as the participant of the reaction, basically a homogeneous catalyst, then it can change the composition of the vessel, but it cannot change the equilibrium constant. This was direct PYQ of JEE Mains. This is the effect of change of volume or pressure. If the pressure is increased, equilibrium shifts to the side where less gas moles is there, because pressure is compressing the vessel. Like, I'm giving you a physical way to think about it. The pressure is putting pressure. Wow. Basically, pressure is putting pressure on the gas moles, and they are forced to, get smaller, like smaller in number. So they shift to the side which has less gas moles to accommodate the pressure. And vice versa, if pressure is decreased, it shifts to the side with more number of gas moles. And the volume has just the opposite effect of pressure. And keep in mind, no effect is there if delta n is equal to 0. These are three cases which I told Gemini to show you, and just look over these. And finally, the effect of addition of inert gas. If inert gas is added at constant volume, no effect is there. And if it is added at constant pressure, it shifts in the direction with, I messed up again. It shifts in the direction with more number of gas moles. And of course, if it shifts in that direction, the moles of that side increase. But concentration of every participant decreases, because at constant pressure, the volume increases if you add inert gas. This is again a direct PYQ. Remember, concentration of every participant decreases, even if moles of one side increase. Okay. So we are done with equilibrium. Here's some extra NCERT info for you. I will be giving the notes. Do read them, and you now no longer need to read the NCERT as well. So congrats. We are done with chemical equilibrium. Thank you for sticking around, and if you like the video, please like and subscribe. Your like and subscribe can help me fund my college fee. We are close to monetization, and please share the video. Bye bye.